in most real-life problems involving differential equations, you can't actually get an explicit solution for the function you're trying to find. So there's a method of approximation called Euler's method that we're going to take a look at. So let me just consider this for a moment. Consider the following equation. xy equals 2. Now, if I take the differential of each side, of course the right side will become 0, and the left side will become x dy plus y dx. What I'm going to do, like you've done in calculus before, is solve for dy over dx. So the first thing I'm going to do is subtract y dx from both sides. Now, I'm not going to try to separate the variables just right now. I am, though, going to get dy over dx by itself on the left. So I'm going to divide by dx. And then I'm also going to divide by x. So I get dy over dx equals negative y over x. So what you have then is the form that we have. So the form of this last equation is dy over dx equals some function of two variables that I'll call f of xy. And you can see right there, f of xy is equal to negative y over x. So, but this is the format of the equation. These are the kind of equations that we're going to be solving. So, and by that I mean to figure out what y was before we took its derivative. So what we're going to do is, I'm going to call this an example 1. And it will go solve dy over dx equals negative y over x. And we know that, let me go back to the original equation. If y is equal to 2, x is equal to 1. So I'm going to say that y of 1 equals 2 is an initial value. Now, I am going to hold off on this. I know we know how to solve it. In fact, I know where it came from. But I want to demonstrate the method of the Euler's method on one that we know, and then I'll work on one that we don't know. So here's the idea behind Euler's method. You have some sort of a curve, y equals f of x. Say it goes something like this. Whatever, it really doesn't matter. And you know information like this about it. More appropriately, you know this information about it. So suppose dy over dx equals f of xy, and y of x naught equals y naught. So this is your initial value, and you have the derivative is equal to some function of two variables. So what you do is locate x naught, y naught. It'll be on the curve itself, since this information is an initial value of the curve itself. What you'll do is compute the derivative at x naught comma y naught. And you'll get some sort of a slope. And what you're going to do is you're going to draw the tangent line from emanating from that point. So draw the tangent line at x naught comma y naught, and you'll get something. This line here was parallel, or it is the tangent line at that particular point. The next thing you're going to want to do is let x1 equal x0 sub 0 plus h. What I'm doing here is I am incrementing incrementing x naught by h. So let me go ahead and put this point here. I'll label it now. We have x sub 0 and we have y sub 0. There's our starting point. Then I'm going to move over till I get to x sub 0 plus h. Now locate x sub 0 plus h on the tangent line. So go up to, go up from x naught plus h to the tangent line. All right, then compute f of x naught plus h, comma, y1, where y1 is the y value on the first tangent line. All right, so from here we go up and I locate my point, and that gives me coordinates x sub 0 plus h. And the y value now, I want you to think about how the y value is gotten. You start at a point x sub 0, comma, y sub 0. Okay, now you're going to go over h units. Up from there, you're going to travel h times the slope and that there will give you your x1, comma, y1. Now, at that point, you're going to do the same thing again. So this here was y sub 0 plus h times f of x sub 0, y sub 0. This is what I'm calling x1. This stuff is x1. And this stuff right here is y1. Now at that point, we do it again. I find the slope at this particular value of x1 and y1 plugging them into f of xy, which also happens to be the slope on the curve itself. So it's going to give you the slope at x sub 0, which means that, or x sub 0 plus h, which means that the slope it's going to calculate will be x sub 0 plus h, but this y1 won't be on the curve. The x sub 0 plus h, of course, will have a location somewhere on the curve. But it's at this point that I'm going to draw another tangent, like so. And look how close it is. It's sort of mimicking the function itself. And then I'm going to do the same thing again. My next one will be x1 plus h, and my new y value will be y1 plus hf of x1, y1. And then from there, I'm going to draw another one. And you can see as we go along, we're going to be modeling the curve with these straight lines. So that's the idea. At each stage, x sub 0 will be given, but for x sub n, that's going to be x sub 0 plus nh. This is how many times we've incremented that. On the other hand, y sub n will be gotten from the previous y value. The h will stay constant because we'll increment a constant amount throughout the whole problem. And the slope, the f function, will be taken from xn minus 1, yn minus 1. So there is the process. Much like Newton's method, this is going to try to give us an approximate solution to the curve. So with that in mind, I would like to go through and do the example one that I said and see how close it comes to the actual answer that we happen to know. So let's come back. Solve is not the right phrase. Approximate. The solution to dy over dx equals negative y over x, and you are given that y of 1 equals 2. So in particular, we're starting x naught equals 1, y naught equals 2. So we'll put that in there. X naught equals 1, y naught equals 2. So let's calculate our y1. Note that x1 equals, now I have to give an increment amount, so I am going to let h equals 0.1. You could let h be smaller if you want to get a better solution, a more accurate solution. You can play around with the h values. So anyways, x1 then will be 1 plus the 0.1, so it'll be 1.1. But y1 I have to get from this formula. Or in particular, y0 was equal to 2, h was equal to 0.1, and the f in this case, the f of xy, is negative y over x. So we're going to have negative y0 over x0. y0 was 2, x0 was 1. So we have 2 minus 0.2 looks like 1.8. And continue as long as you want to get as much of an approximate curve as you want to. So for my x2, I'll increment by 0.1 again, and I'll have 1.2. My y2 will be gotten from y1 plus h f of x1 comma y1. y1 was 1.8 plus h was staying at 0.1 times negative, and here we're going to have y1 over x1. So the y1 was 1.8, and the x2, or sorry, the x1 was 1.1. And at some point, I mean, the decimals are going to get out of hand. Let me go ahead and start our calculator and calculate some of these numbers. All right, let's see. We have 1.8 plus 0.1 times, then we're going to have negative 1.8 divided by 1.1. And that equals 1.636363. I'll put 63 with a bar over it. And you can continue this process. Then we have x3, increment x by 0.1 again, 1.3. Then y3 equals y2 plus hf of x2, y2. And that equals, what was our y2? That was 1.63 with a bar plus 0.1 times negative 1.63 bar over it divided by 1.3. And let's go bring the calculator up and do those. So you can use this number. You don't have to round or anything like that. I can simply go plus 0.1 times, and then I can put the answer again by putting second, and above the minus sign or the negative sign I get answer. But before I do answer, I should probably insert, let's see, second, insert the negative, and then divide that by 1.2. Enter. And believe it or not, that comes out to 1.5. I'm a little surprised, but that's fine. So in this way, you're creating a collection of points that you can possibly graph and then connect them with straight lines. Now, this process is very arduous to do by hand. However, I will have you do a few of these, not a few problems, but a few iterations on a test. Realistically, you're going to have a machine do this stuff for you. In particular, I'm going to do this stuff in a spreadsheet. In fact, I believe I'm going to use Excel. All right, in column A, I'm going to let that stand for my n values. In column B, I'm going to let these be my x sub n, so I'm going to do that. And then in column C, I'm going to do y sub n. Let me make this to full screen so maybe you can see this better. All right, so I'll increment. Well, now n is starting at 0 for the initial value, so I'll do that. And then if I want to increment it by 1, so I want to go n equals 0, 1, 2, 3, what I can do is I can do you want to do equals a2, that's the 0 highlighted there, plus 1. If I hit enter, of course, it'll put 1. Now, the nice thing about this is I can copy this cell and then go down as long as I want. Say I want to go up to like 30, let's see, 31, and paste. And you see what it did? It incremented them all for me. In fact, I wanted to go to 32 because I want to go for n equals 30. So I'll copy that cell and paste it in there. Now the xn's are easy. The xn's, they start when x is equal to 1, and we increment these by 0.1. So in this case, I'll put equals b2 plus 0.1. And it is incremented. Then all I got to do is copy that cell and paste it as far down as I want to go. And there they are. It goes all the way up to 4. And my yn starts at 2. And the way I want to increment that, of course, is I want to do y1, which is located, well, y0, sorry, the first start is y0, which was the 2, but that was in cell C2. So I'll do C2 plus, then we want to do h, which was 0.1. Then I have to do times, you have to actually put that in there, parenthesis. Now then, we had negative y over x. So in our case, it would be negative y, for this first one, would be negative y0, so I'm going to put C2, and then I'm going to divide by B2. And I'll end the parenthesis, enter. So you can see this is what we got when we did it by hand. So I'll copy and paste this all the way down. And there we've got decimals. Some decimals are good, some decimals are bad. I don't really care about that. What I want to do is I would like to graph this, but I would like to compare it to the original or the real value of y from the function we know to be true to see how accurate this is. So if we go back, that's the whole point of this exercise, is to show you how accurate this method is. If we go back to the original problem itself, we knew what was the y value. The y itself, the solution to this problem here, is that y equals 2 over x. That's the solution. So I'm going to plug that in to the Excel spreadsheet, and let's call it the real space y. Let's call it real y. And that's equal to 2 over x. So the first thing I'm going to do is equals, and I am going to do 2 divided by, the x is located in B2, enter. I get 2, of course, that's the starting value. and I'll copy and paste this all the way down. Now, if I want to see how bad the error is, like let's call it, there's be two columns here. Let's call this the absolute error. And that's simply where I take y minus the yn, or better yet, the absolute value of that. So what you can do, I think ABS is, yes, that's absolute value. So we'll have that, and I'm simply going to do D2 minus C2. This gives me the absolute error of our thing. And of course, they're going to start correct. So you can see these are the errors, and as it goes farther and farther down, well, sometimes they're worse and sometimes they're better. It doesn't look like, it looks like in here is the worst chunk of them. Let's get another column called the relative error. This is really the percentage error, and I would like to know if I take the error that I have and divide it by the real y value and then multiply it by 100%. So this one, I will take E2, and then I'm going to divide it by the real y value, so that'll be D2. But then I have to multiply it by 100%. So I should, I moved something I should not have. What I should probably do is put my 100 over here and times. Of course, there's no error in the original one. And now we'll see, as a percentage error, let's see what these are. How bad can they be? And here, so here's our errors. You can see that the error, the relative error does get worse. We're off by 1%, then 1.8%, 2.5%. And as we stray farther away from the beginning point, the error gets worse and worse. Now, I will mention, but I will not do a better method that gives much better results than what we're using here. In fact, the textbook that we're using tells me that no serious practitioner of differential equations actually uses Euler's method, but processes like it are used to get much better solutions. Well, let's take a look. What I want to do now is I would like to graph our thing versus the real one and see how far they actually deviate from each other in a graph. So to do that, I'm going to have to enter a chart. So let's insert a chart. I think the one that I had the best luck with was the scatter chart. So I'm going to do a scatter, but I would like to connect the dots. I don't want to do smooth, well, you could do smooth lines, but technically speaking, we'll have a scatter plot with straight lines. Now the question is, where's the data going to come from? There it is, select data. All right, so we're going to select our data. Let's go ahead here. And I think I can do this for xn and yn. And it does a lot of the work for me. So you can see it formats it and everything very nicely. And now I would like to add some more data, but this time I would like to put the x values and the real y values and see how close they are. Okay, so what I have here are the two curves graphed together. Let me see if I can copy this thing. So here's what I have. After computing all those data values, the red one, that is equal to y equals 2 over x, and the blue one is the approximate y. And you can see that it strays a little farther and farther as we go along. The reason why these look like curves and not straight elements is because my increment is only 0.1. It's very small, and so perhaps it's just not something that is easy to see. And it's possible some smoothing was done in the program itself anyways, but you can see that it's a little bit off, and that's the best we can hope for with this particular method. Now let's work a problem that we do not know the solution beforehand. And that simply looks like this. We're going to have, we'll approximate y prime equal x squared plus y squared, y of 0 equals 1. So let's go through the process and see what happens. Remember, this is dy over dx equals f of x comma y. And x sub 0 equals 0. Y sub 0 equals 1. And you can choose whatever h value you want. Usually it'll be given to you. I am going to do h equals 0.5. Actually, I want to go a little better. 0.5 is pretty bad. 0.05. So half of what it was before. Let's go ahead and start getting our values then. So x1 is going to equal 0.05. And the x's are easy to do. y1, once again, is going to be y sub 0 plus h f of x sub 0 y sub 0. My y sub 0 was 1. The h was 0.05. And the x and y, x0 was 0, so we're going to have 0 squared. The y0 was 1, so we're going to get plus 1 squared. And that equals 1.05. So that's easy enough. Now let's move on. x2 will be 0.05 plus 0.05, so I'll have 0.1. y2 will equal y1 plus h f of x1 comma y1. So my y1 was 1.05. My h, of course, was equal to 0.05. And then my x1 was 0.1. So I have 0.1. I'm sorry, x1 is up here. 0.05 squared plus, and the y was 1.05. And so that gives me, I'm not going to do this by hand. I'm going to let calculators do most of my work. In fact, after the next one of these, I think I'm going to go straight to my Excel spreadsheet anyways. So let's see what we have here. We have 1.05 plus 0.05 parenthesis 0 or 0.05 squared plus 1.05 squared. And that gives me 1.10525. And so you get the idea. Here we go and get those. I think what I am going to do is go into Excel. I'm going to leave all that's good there. I'll pick a new sheet, I think. And I think that I will do like I did before. I'll start n equals 0, and then I'll add 1 to it and then increment that way. So I'll say this equals A2 plus 1 to get our n values. Copy that and then paste for a while. I'm not going to do a lot. Let's go up to 20, I guess. And then my x sub n, we had x sub 0 was 0, and then we're incrementing these by 0.05 each time. So what I'll put for the next one is b2 plus 0.05. That'll give me my increments, and I'll go ahead and throw them in. And then y underscore n, y started at 1, and then of course its increments were y, so this would be y0. y0 is located in c2 plus 0.05 times, and in parentheses I'll have to put x sub 0, so this will be b2 squared plus c2 squared, and then end the parenthesis. And did we get 1.05? Yes, we did last time. So then I'm going to start copying, Control C, and then paste, Control V. And those are my numbers. If I actually want to see something of a curve, I'll insert a chart. And in this case, I will insert, it says recommended charts. I don't care about that. I'm going to pick a scatter chart. And I'll get to choose my choice, make my choice here. It really doesn't matter. I don't think I want the dots to be on there because they're big and bulky. I'm just going to use the ones that have straight line connectors. And now what you got to do is tell it what your data is going to be. So you select your data. I right click, by the way. And my data source then, all I got to do is start xn in that's location x0, move to the right to include y0, and then scroll down. I believe Excel will automatically make the left column x's and the right column y's. We'll take a look. And there you go. It certainly looks like the case. It looks like the x values are down here and the y values are along there. And there you go. You have your solution curve or approximate curve. And you can see it's sort of jaggedy to indicate the straight lines. But what you might be asked then, or what are the approximate values of this or that? Say like they wanted to know, well, like what is y of 0.5? Well, your estimate would be 1.933181. If you were asked to grab it, there it is. I do not have a solution curve that I know for this particular problem, so we had to use this method to approximate the curve. And there you go. Let's go ahead and throw that in. I believe I can just Control C to copy it and come back to this thing. Control V. There it is, and of course it's way smaller than is necessary, so we'll stretch it out. One thing about using this software program, I think that I can do editing and things like that from here. Probably make that a big fat no. You can't do anything there. But you get the idea. This is Euler's method. It's a simple way, something like Newton's method, to get an approximate answer. Now, Euler's method is not used professionally. The only reason I'm mentioning that is better methods have been used. In fact, the method that the books that I read have decided was the best way of doing these kind of problems are referred to, let's call it the best method so far, is referred to as the Runge-Kutta method, and I think it's the 4th generation. They must work on these and improve them slightly as time goes on and on. Some books simply refer to this as RK4. Maybe in 10 or 20 years there'll be an RK5 that's even a little bit better, but for now this is what you have. If a student are interested in this stuff, the Runge-Kutta method is usually found somewhere near the last part of an ordinary differential equations book. I don't know if they go through the effort of proving anything, but I believe they at least step you through the process. So I'll end it there. I think I've done enough for you to get the idea on how to proceed on these types of problems.